Hello friends, welcome back to the another video lecture of ADS subjects. In today's video lecture, we are going to learn about articulation point in given graph. So, for the articulation point, definition says, let G of V and E means a graph with vertex V and edges E be a connected undirected graph, means that graph will be connected as well as that will be undirected. Then an articulation point of graph G is a vertex whose removal disconnect graph G. So that type of vertex will be known as articulation point. Let's understand it by an example. If we have this type of graph, then this graph is connected as well as undirected. So we will have to find out that vertex whose removal will made a disconnected graph G. So here in this example, if we remove this vertex C, then our graph will become unconnected, means this portion ABD and another portion is EFG. So this is a unconnected graph. So in that case, our point C or vertex C will be known as a articulation point. Now, what is the need of this articulation point? For example, in communication network, the node or vertices represent the communication station C. If this communication T is an articulation point, then failure of this station make the entire communication system down, and this is surely not desirable feature. For example, if we have this C as an articulation point and in communication network C fails, then these nodes will not communicate with this type of E, F and G nodes. Then this entire communication system will be down because of only single point C. Then that is the need of finding the articulation point. Now main question is that how we can find out that articulation points. There are certain steps to find articulation point. First step says prepare a DFS, means depth first search tree of given graph and give DFN to each vertex, where DFN is depth first search number, that we will understand by examples. Another step says add back edges. Third step says find low of each vertex. Step number 4 says if DFN of U is less than or equal to low of W, then U is the articulation point, where U is parent and W is child. Okay, so after implementing all these steps, in step number 4 we can find the articulation point, and we will have to remember these two things. That first thing says the root node of the DFS tree is an articulation point if it has 2 or more children, or a leaf node of DFS is not an articulation point anywhere. Okay, so let's find out articulation point by an example. So we have this type of example. Here we have a graph. In that we have to find out articulation point. So our step number 1 says prepare a DFS tree of given graph. So for preparing a DFS tree, we will have to select a starting point. Then we will have to find out other nodes. We have these nodes A, B, C, D, E, F and G. If we start from the node number A, then A has 2 adjacent vertices C and B. If we select any one vertex, here we have selected A to B, then our DFS tree says we will have to find out adjacent node of B. So B have only one adjacent node, D, so we will connect B to D. Now our DFS says find adjacent nodes of D. So D have only one adjacent node, which is C, so connection of D to C. Now we will have to find out adjacent node of C. So C have three adjacent node, A, E and F, but A is visited node, so we cannot go from C to A. Two unvisited node available from C. If we select from C to E, then in next step we will have to find out adjacent node of E. So adjacent node of E is G. Next step we will find out adjacent node of G. So adjacent node of G is G to F, and from F we can go to C, but C is already visited. Then this is the DFS tree of this given graph. Next thing is we have to give DFN to each vertex. DFN means depth first search number, means in which manner we have construct our DFS tree. So first of all we have visit node number A, our root A, so that will be the depth first number 1. After A we have visited B, so B will be DFN 2. After B we have visited D, so that will be 3. After it C, then that will be 4. After it C we have E, so DFN is 5. For G DFN will be 6, and for F DFN will be 7. So this is the step number 1. We have prepared a DFS for given graph and also assigned DFN to each vertex. Now our step number 2 says add back edges. Here the back edges that are available in original graph but not in DFS tree. Okay, so here we have a DFS tree here and our original graph is here. So here we can observe that we have two edges that is not available in our DFS tree. First is C to A and second is F to C. So that are the back edges, and rule says that must be higher DFN to lower, means here edge between A and C, but higher DFN is 4 and lower DFN is 1. So edge will be C to A. Here C has DFN of 4 and F has DFN of 7. So edge will be F to C. So this is the back edges. So this is step number 2. We have added back edges in our tree. Step number 3 says find low of each vertex. We have to find out low. So low is lowest DFN that can be reached from a vertex by taking one back edge. Now we will have to find out low. So we will have to find out DFN that can be reached from vertex by taking one back edge. So no need to find out low for this our starting node because it have already DFN 1, no lower DFN available than 1. So we will start with the node B. So here from the node B, if we go in this direction, then B to D, D to C, and here we have one back edge, and from that back edge we will go to the end, and there is a DFN of 1. Then low of B will be 1. If we find out low for D, then for D, if we go from D to C, and from C we have a back edge to A, and A's DFN is 1. So low of D will become again 1. For the C, if we go from the back edge, then we will have node A, and DFN of A is 1. Then low of C will become 1. For E, if we find out low, then from E we can go to G, from G we can go to F, and there is a back edge, and that back edge is to C, and C's DFN is 4. That's why our law of E will become 4. For the G, if we find out law for G, then we will go from G to F, and from F we have a back edge to the C, and this C DFN is 4. So law of G will become 4. If we find law for F, then from F there is a back edge to C, then DFN of C is 4. So law of F will become 4. So this is the identification of law of every vertices. Now in step number 4, if DFN of U is less than or equal to law of W, then U is the articulation point. Means in this step we will find our articulation point. So definition says DFN of U, so U is our parent, and law of W, W is our child. So no need to find out for root node. We will start from the node B. So for B and D, if we find out, then DFN of B is less than or equal to law of D, then equation says it will become 2 less than or equal to 1, then condition will be false. For the next pair C and D, if DFN is D less than or equal to law C, then that will become 3 less than or equal to 1, that will be again false. From C and E, DFN of C is less than or equal to law of E. Here DFN of C is 4, and law of E is also 4. So here this condition is true. It means C is our articulation point. There can be one or many articulation point in graph, so we will have to find out this condition for the every vertex. So we will check for the vertex E and G, then it will become 5 less than or equal to 4, again condition false. If we find for G and F, then it will become 6 less than or equal to 4, again condition false. So from the all vertices we have found that C is our articulation point in given graph. Okay, so this is the example for finding articulation point in our graph. Our next topic is bi-connected graph. A graph G is said to be bi-connected if it contains no articulation point. For example, if we have this type of graph that is connected as well as undirected. So if we remove any single node, we do not have disjoint graph, so it is called bi-directed graph. Okay, so this type of graph will be bi-connected, or we can say bi-directed graph. Now bi-connected components. If we have this type of graph and it have many articulation points, here we can see we have 2, 3 and 5 articulation points. So with the articulation point 2, 3 and 5, we can get these separate components of different graphs. So this component will be known as bi-connected components. Okay, so this is it for today's topic. If you like this video, then like, comment and subscribe. Also share it with your friends. Thank you, friends.